equipotential gradient. Now we know that if we have a positive charge here, then this will create an electric field around space, and the electric potential usually will decrease in the direction of the electric field. The electric potential will decrease in this direction. This we have known from the concept of electric potential. So if we have 2 points here, A and B, then the potential at point A will be greater than the potential at point B. This we have known from the concept of potential, electrostatic potential. So we can see that the potential varies as we increase the distance from this point charge. So if we increase the distance r, suppose this is your r and it is a variable and you're increasing in this direction. Your r increases in this direction. Then the potential also decreases in the same direction as the direction of the electric field. So mathematically we will express this decrease in the potential with respect to r as minus ddr of V. So minus here indicates the decrease of potential. If there's no minus, then this formula here means the potential is increasing in the direction of r. But if you put a minus sign here, then this indicates the decrease in potential V with respect to the distance r. So as you're increasing r, the electric potential decreases. And this minus ddr of V, this is known as the potential gradient. And this potential gradient is equal to the electric field intensity E. So here the electric field intensity is equal to the negative of the potential gradient, which is the ddr of V. So using this formula we can find the relation between the E and V. Now suppose V is given as 1 by 4 pi epsilon naught Q by R. Suppose V varies as this formula. Now 1 by 4 pi epsilon naught is constant, Q is also say a constant, is a positive charge constant, and this R, it varies, okay, it's a variable. So your V varies as R. So if R increases, V decreases. So we can put this formula here. What we'll get is minus ddr. Instead of V, I'll put 1 by 4 pi epsilon naught Q by R. So now 1 by 4 pi epsilon naught Q, they are constants. So what we have is this formula, Q 4 pi epsilon naught. We only take the derivative of 1 by R. And this 1 by R, I can write it as r to the power minus 1. Now using this mathematical formula, or the derivation of this r minus 1 will be equal to, so using this formula, I'll show you the formula first. If we have ddr of r to the power n, then this will be equal to n r n minus 1. Okay, so this is the formula which we are going to use. ddr of n r to the power n is equal to n times r to the power n minus 1. So here this n is equal to minus 1. So ddr of r to the power minus 1 will be, instead of n I'll write minus 1, then r minus 1 minus 1. So this is the result. So here we have minus 1 minus 1, this will give you minus 2. r to the power minus 2. Then this r to the power minus 2 I can write this as r to the power 2, and minus and minus will cancel. So this one and this one, you can cancel it, and what we're left here with E is equal to, I can put Q here, so 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught Q divided by R square. So knowing the potential, we can get the electric field intensity also using this formula, potential gradient, and this we have derived in chapter 2. So this is the relation between the electric field intensity and the electrostatic potential. Now, equipotential surface. Now this is similar to the Gaussian surface. If you can recall in chapter 1, the Gaussian surface is a surface in which the electric field intensity is same everywhere on the surface. Similarly here also, equipotential surface is a surface in which the electrostatic potential is same everywhere on the surface. For example, say we have the surface of a sphere. So we have a sphere. So this is a sphere, it's having a radius r, and say at this point, at the center, we have a positive charge plus q. So we have a positive charge at the center of the sphere of radius r. Then the potential at this point on the surface, say this A, at point A, the potential is given as VA is equal to 1 by 4 pi epsilon naught. This is the potential due to a point charge. So Q divided by R, which is the distance of this point from the center, or from the charge plus Q. So this is the potential at A. And if you take another point here, B, then again here this distance will be the radius. This point B is on the surface of the sphere, so the distance here is again R. So the potential at point B, this will be equal to 1 by 4 pi epsilon naught Q divided by R. So here you can see that VA is equal to VB. So this surface of a sphere is known as the equipotential surface. So we have the equipotential surface here. Okay, so an equipotential surface is a surface on which the potential is same everywhere on that surface. And for example, here is the surface of a sphere which encloses a charge plus q at its center. Now we come to the properties of equipotential surface. Now the equipotential surface has some properties. Number one is that the work done, suppose if we have this equipotential surface here, and say these are 2 points on the equipotential surface, A and B. Then the work done in the bringing any charge from one point of the equipotential surface, say A, to another point of the equipotential surface, say B, will be equal to 0. So the work done, if we have a charge Q, and if you bring this charge Q from A to B, then the work done will be 0. Now this can be proven from the potential difference, the definition of the potential difference. So here if we have 2 points A and B, then the potential difference, say VB minus VA, this is defined as the work done in bringing a charge from A to B per unit charge. Now since the potential is same, VB on the equipotential surface, the potential is same, so VB is equal to VA. So here the difference will be equal to 0. So here we have work done from A to B divided by Q, and this implies that now Q cannot be equal to 0, so here we have WAB to be equal to 0. So this implies that the work done in bringing a charge from point A to point B is equal to 0. So on the equipotential surface, the work done is equal to 0. So that is one property, the first property. The second property is that the electric field is always perpendicular to the equipotential surface. So the second property is that the electric field is always directed perpendicular to the equipotential surface. So again here we consider an equipotential surface, and you have 2 points A and B. Suppose we are displacing, say, a test charge from this point A to point B. Now through a small displacement dl. Okay, so here we're displacing a test charge from A to B through a small displacement dl. Then the work done in displacing the test charge will be given as WAB, and this is equal to the force dot the displacement dl. So the dot product of the force and the displacement. Now the force is given as Q naught E, then dot dl. Remember, we're displacing a test charge Q naught. So here we have Q naught E dot dl. Then from property number 1, the work done on the equipotential surface is always equal to 0. The work done in displacing a charge on the equipotential surface is always equal to 0. So this work done is equal to 0. So this implies that your E dot dl, since Q naught cannot be equal to 0, so E dot dl will be equal to 0. Remember, this is from property number 1. So we have E dot dl, then we have E dl cos of theta. This is equal to 0. Now E cannot be equal to 0, dl cannot be equal to 0, so this implies that cos theta is equal to 0. So here this angle will be equal to 90 degree. So cos of 90 will be equal to 0. So this implies that the angle theta is equal to 90 degree. Now theta, what is this? Theta is the angle between E and dl. So if your dl is in this direction, then your E will be in this direction. So this will be the direction of E, which is 90 degree to dl or to the equipotential surface. So this is the second property, that the electric field is always normal or perpendicular to the equipotential surface. Now the third property. Now we come to the third property. The third property says that where the electric field is stronger, the equipotential surface is closer together, and where the electric field is weaker, the equipotential surface, they are farther apart. So for example, if we have a positive charge, now the electric field will always be directed away from the positive charge. Now if I have to draw the equipotential surface in this case, then I shall draw a sphere which is enclosing this charge, and this charge is at the center of those spheres. So we have the first equipotential surface, then we have the second equipotential surface, then we have the third equipotential surface, okay, so these are the equipotential surface, the first one, the second one, and the third one. Now here, from the properties of electric field lines, the electric field is stronger in this region. So here you can see in this region the equipotential surface, they are closer together, and the electric field intensity is weaker in this region. So here you can see the equipotential surface, they are farther apart. Okay, so here they are very close to one another, here they are farther from one another. So that is the third property of the equipotential surface. Now we can consider the two surfaces here. The surface number 1, I'll write here 1, and this is surface 2. Now say the distance between them is delta r. Okay, so delta r here, this distance I'll write it as delta r. Here is the spacing between the two equipotential surfaces. So delta r here is the spacing between the surface. Spacing between the equipotential surface. So here I'll just write the surface. So delta r is the spacing between the surface, and say the potential at on the surface is Vi, and the potential on the surface is V2. Then the potential difference is denoted by delta V. So delta V here is equal to, say, V2 minus Vi. Okay, so there's a potential difference between the two surfaces, and that potential difference is given as delta V. Hence your E, this will be given as delta V by delta R. Okay, so we can have a minus here to indicate that E, or the potential, decreases in the direction of E. But in magnitude, I'll just write as, in magnitude, delta V by delta R. So here you can see that if delta R is small, the electric field will be large, and if delta R is large, if the spacing is large, then the electric field will be small. So which is the case here also. If this del R is small, E will be large, and if del R is large, E will be small. So that is the third property of the equipotential surface. Now the fourth property is that no two equipotential surfaces can intersect one another. So you cannot have say one equipotential surface like this and another one like this. So this cannot be the case. Okay, so if we have an equipotential surface, they cannot intersect one another. Just like electric field lines, they cannot intersect one another. Equipotential surface also cannot intersect one another. So that is the fourth property.